The night sky, vast and mysterious, is a celestial ocean studded with millions of stars. Each one of those stars is a sun, just like our own, and our sun, with all its brilliance, is but one among billions within a single galaxy. And that galaxy, the Milky Way, is just a tiny part of an even grander universe, teeming with countless other galaxies and their stars. But as awe-inspiring as this cosmic canvas is, it carries with it a sobering truth. Everything, even this grand spectacle, must come to an end someday. The question looms: how will this universe, in all its splendor, meet its fate? Will it burn out in a fiery cataclysm, or will it slowly fade into the void, extinguishing itself over eons? This question has puzzled scientists, philosophers, and dreamers for centuries. But what if the end of the universe is already written in the very fabric of space and time? To answer this, we must embark on a journey into the unknown, into the depths of dark matter, dark energy, and the incredible phenomena of black holes that govern the cosmos. Together, we'll search for the truth about the universe's ultimate fate. When you look up at the night sky, it's easy to feel small and insignificant. After all, Earth is just one tiny speck in the vast expanse of space. But when you examine the universe with a deeper lens, Earth takes on a new significance. We orbit a star that, despite being ordinary by cosmic standards, sustains life on our planet. Our sun is part of the solar system, which in turn resides in the Milky Way galaxy, a swirling, majestic collection of hundreds of billions of stars, many with planets of their own. The Milky Way itself is one of the most spectacular features of the universe, a magnificent spiral galaxy located in a cosmic sea of even more galaxies. Our sun, along with Earth, orbits within the Orion arm of this galaxy, a region approximately 26,000 light-years from the galactic center, where a supermassive black hole sits, a powerful force exerting its immense gravitational pull. Though this distance may seem mind-boggling, it's only a small part of our cosmic neighborhood. Beyond our galaxy, there are many others, over 100 billion in fact, each one a universe unto itself, filled with stars, planets, and potentially life. As we zoom out even further, we find ourselves within the local group, a collection of galaxies that includes our Milky Way, Andromeda, and over 50 smaller galaxies. This group is only a small fraction of the Virgo supercluster, a massive conglomeration of galaxies stretching across a staggering 110 million light-years of space. And this supercluster is just one piece of the even larger Laniakea supercluster, a structure so immense that it spans over 500 million light-years, encompassing hundreds of thousands of galaxies. We are but one small part of a universe that is constantly expanding, and yet the question remains: how will it all end? To understand the true scale of the universe, let's shrink 13.8 billion years of cosmic history into a single year, an exercise known as the cosmic calendar. In this calendar, each second represents about 437 years, allowing us to grasp the enormity of time. January 1st marks the Big Bang, the explosive birth of the universe, setting the stage for everything that follows. The first stars appear by the end of January, and by March, galaxies begin to form, pulling together the material of the universe into organized systems. The Milky Way galaxy takes shape in May, and by August, our solar system begins to form from a vast cloud of gas and dust. Earth, the planet we call home, coalesces soon after, but it isn't until September that it cools enough for the first signs of life to take hold. By December, the pace of events quickens. Complex life forms evolve in the oceans, and by December 17th, the first plants make their way onto land, followed by the reign of the dinosaurs, which lasts until December 26th. In the final moments of the year, mammals begin to thrive, and by the last few seconds of December 31st, humans appear, an incredibly brief moment in the context of cosmic time. The entirety of human history, from the rise of civilizations to the digital age, unfolds in the final few seconds of this cosmic year. It's a humbling thought, reminding us of how brief our existence is compared to the age of the universe. The origin of the universe is best understood through the Big Bang theory, a groundbreaking concept that suggests the universe began as an infinitely dense point, approximately 13.8 billion years ago. This singularity exploded outward, sending matter and energy hurtling into the void, where it expanded to create the universe as we know it today. But this isn't just a theory. It is supported by an overwhelming body of evidence. Observations of distant galaxies show that the universe is still expanding, and the cosmic microwave background radiation, the faint glow left over from the Big Bang, provides a snapshot of the universe's earliest moments. This discovery has helped scientists trace the origins of the universe and its evolution from a hot, dense state into the vast, cold cosmos we observe today. As we peer deeper into the mysteries of space, we realize that the universe is governed by forces and phenomena that are still largely unknown to us: dark matter, dark energy, and black holes. These cosmic entities, hidden in the very fabric of reality, hold the keys to understanding the universe's past and its ultimate future. As we look to the stars, we wonder, will the universe continue to expand indefinitely, or will it collapse in on itself? Will it meet a violent end or fade away quietly? Only time will reveal the answers. But one thing is certain: the journey to uncover the universe's fate is just beginning. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, CMB, a faint afterglow of the universe's explosive birth. Discovered by Arno Penzias and Robert Wilson in 1964, the CMB is a nearly uniform wash of microwave radiation that permeates the entire cosmos, detectable from every point in the sky. This discovery was not only a monumental breakthrough, but also a decisive moment in the validation of the Big Bang theory. The uniformity of the CMB, combined with its slight ripples or variations, aligns precisely with what would be expected if the universe had originated in a hot, dense state, rapidly expanding from an initial singularity. The variations within the CMB offer scientists a crucial window into the structure of the early universe, revealing the distribution of matter that would eventually give rise to galaxies, stars, and vast cosmic structures. These ripples, often described as the faint echoes of the universe's infancy, tell a story of a cosmos that was once far more uniform but gradually cooled and expanded, setting the stage for the creation of all that we see today. Another foundational pillar of the Big Bang theory comes from the observation of the universe's continuous expansion. Edwin Hubble's groundbreaking discovery in the 1920s that galaxies are moving away from us and more distant ones are receding faster, forever altered our understanding of the universe. This discovery was analogous to dots on the surface of an inflating balloon, where each dot moves away from every other dot as the balloon expands. Extrapolating this phenomenon backward in time suggests that the universe was once infinitely small, hot, and dense, and began its expansive journey from a singular point in the distant past. This expanding universe, stretching ever further, paints a vivid picture of a dynamic and evolving cosmos. The recognition that the universe is not static, but in perpetual motion, challenges us to rethink our place within this ever-changing vastness, underscoring the theory's power to explain the universe's current and past states. The abundance of light elements in the universe, hydrogen, helium, and lithium, further strengthens the case for the Big Bang. Theoretical predictions based on the early universe's hot, dense conditions anticipated the formation of these elements in specific proportions. Remarkably, these predicted abundances align closely with what we observe throughout the cosmos today, further validating the Big Bang theory. This alignment is a key piece of empirical evidence confirming that the conditions of the early universe were indeed conducive to the formation of these elements in the quantities observed. Just as the cosmic microwave background radiation and the universe's expansion provide crucial support for the theory, the chemical composition of the universe provides a final, concrete affirmation that the Big Bang theory offers the most consistent and reliable explanation for the origins of the cosmos. In the saga of the stars, there exists an awe-inspiring narrative of birth, transformation, and eventual death, a cycle that governs the life of every star, including our own sun. This journey begins in the cold, dark depths of molecular clouds, vast, dense regions filled with gas and dust, where the forces of gravity work relentlessly to gather material. Over time, these pockets of gas become increasingly dense and hot, eventually reaching the conditions necessary for nuclear fusion. This ignition marks the birth of a star, a process that heralds the beginning of the main sequence phase, where hydrogen is fused into helium in the star's core. For a star like the Sun, this phase can last for approximately 10 billion years, during which the forces of gravity and nuclear fusion maintain a delicate balance. The energy produced by fusion radiates outward, giving the star its light and warmth and sustaining life on planets like Earth. But as the star's fuel is exhausted, the peaceful phase of fusion comes to an end, and the star begins a dramatic transformation. The core contracts, becoming denser and hotter, while the outer layers expand and cool, transforming the star into a red giant. During this phase, the star's diameter swells to immense proportions, and if the Sun were to enter this stage, it would likely engulf the inner planets, including Earth, vaporizing them in the process. At the core of this red giant, helium fusion begins, creating heavier elements such as carbon and oxygen. This fusion, however, is not enough to maintain the star's stability, and eventually the outer layers are ejected into space, forming a planetary nebula, a stunningly colorful cloud of gas and dust. What remains is the star's core, a white dwarf, an incredibly dense, Earth-sized remnant with a mass close to that of the Sun. The final stage of this cosmic journey is marked by the gradual cooling and fading of the white dwarf, which will take trillions of years. Over this immense timescale, the star's life will conclude, not with a dramatic explosion, but as a quiet, cold, and dark relic of what once was. This process reflects the inevitable fate of many stars, including our Sun, whose journey through the cosmos will ultimately lead it to a state of silence and stillness. As our Sun continues its journey towards becoming a red giant, the transformation will not only reshape the star itself, but also have profound consequences for the planets that orbit it. Over billions of years, the Sun's increasing size and decreasing surface temperature will radically alter the dynamics of our solar system. The inner planets, Mercury, Venus, and even Earth, will face catastrophic changes. As the Sun expands, its intense heat and gravitational forces will likely engulf the inner planets, vaporizing them entirely. This transformation will mark the end of the planet's existence in their current forms, underscoring the ephemeral nature of planetary bodies in the grand cosmic cycle. Yet, even in this destruction, there lies a beauty in the inevitability of the star's evolution, reminding us that change, while often destructive, is an inherent part of the universe's ongoing story. Earth's future is a story of delicate balances, a journey of immense transformations. Although its fate remains uncertain, the path ahead seems perilously set. The Earth may narrowly escape being swallowed by the expanding Sun, yet its survival will come at a steep cost. As the Sun grows increasingly unstable, it will unleash a fierce wave of heat, drastically raising temperatures across the planet. This extreme heat could strip away the atmosphere, a crucial protective shield that sustains life. Oceans, once teeming with life, would evaporate into the air, leaving behind a barren, lifeless landscape. Earth may survive, but it will no longer be the vibrant, life-filled planet we know. The Earth will become a scorched shell of its former self, a silent reminder of the once thriving world that was. Yet as Earth faces this cataclysm, Mars, positioned slightly further from the Sun, will undergo its own series of profound changes. The increase in solar radiation will warm the Martian surface, possibly creating conditions conducive to retaining an atmosphere. For a fleeting moment, Mars may even see liquid water on its surface again, a rare occurrence in the planet's long, cold history. This would offer a tantalizing glimpse of what Mars might have once been, an environment that could have supported life. However, this phase would be short-lived. As the Sun sheds its outer layers during its red giant phase, its luminosity will decrease, causing Mars's brief warmth to dissipate. The distance between the planets will grow, leaving Mars to cool again, so by reverting to its frozen, desolate state. The outer gas giants, Jupiter, Saturn, Uranus, and Neptune, will not escape unscathed either. These colossal planets, so far from the Sun, will see their atmospheres undergo dramatic changes as they are bombarded with heightened solar radiation. Some of their lighter elements may be stripped away, altering their appearance and potentially even their internal structure. These moons, long considered some of the most promising candidates for harboring life, may finally experience a taste of warmth. As the solar radiation increases, the icy surfaces of these moons could begin to melt, allowing liquid water to pool temporarily on their surfaces. For a short period, These moons could briefly become an oasis of life, with the possibility of microbial life flourishing in these newfound liquid environments. But like Mars, this phase will be ephemeral. Once the sun enters its final stages, these moons will be left in a cold, lifeless state once more. As the sun continues to age and loses mass, its grip on the solar system weakens. The gravitational pull that once kept the planets in their stable orbits will diminish, causing their trajectories to shift. This subtle but profound change will lead to orbital resonances, where the orbits of planets and moons adjust in response to each other. The solar system's dynamics will be forever altered. Comets and asteroids, once confined to the Kuiper Belt and Oort cloud, will be dislodged from their ancient orbits. These icy bodies will be sent spiraling through the solar system, their paths reshaped by the weakened influence of the sun. The result could be chaos, with some of these objects potentially colliding with planets or being cast into the depths of space. In the aftermath of the sun's death, it will transform into a white dwarf, a cold, dim remnant of its former self. The remaining planets, now adrift in an increasingly colder universe, will orbit this faint star, receiving only a fraction of the warmth they once enjoyed. The solar system will have undergone a dramatic metamorphosis, evolving into a quiet, desolate place where light and life are but distant memories. Yet, despite this stark silence, the solar system's transformation will stand as a tribute to the sun's once vibrant existence, a final chapter in the celestial story of life, death, and rebirth. The death of a sun-like star does not signal the end of creation. Instead, it marks the beginning of one of the most awe-inspiring spectacles in the universe, the formation of a planetary nebula. As a star exhausts its nuclear fuel, it begins to shed its outer layers into space. The remnants of the star, now a hot, dense white dwarf, emit intense ultraviolet radiation which illuminates the expelled gas. This process creates a breathtaking cosmic display, with the gas glowing in a kaleidoscope of colors. These nebulae can shine for thousands of years, offering a stunning testament to the complex cycles of stellar life. The name planetary nebula is, in fact, a misnomer. Early astronomers mistakenly thought these glowing clouds were planets. In reality, they are vast, luminous clouds of ionized gas, each a magnificent reminder of a star's final days. The shapes and structures of planetary nebulae are varied and intricate. Some take the form of symmetrical rings or shells, while others twist into spiral shapes or complex, irregular patterns. These diverse forms arise from the interaction of the stellar wind, magnetic fields, and the surrounding interstellar medium. Each nebula's color palette is a product of the gases present and the temperatures they reach. Hydrogen glows red, oxygen produces green, and helium and nitrogen can create blues and purples. Some nebulae even feature bursts of yellow and violet hues. The Helix Nebula, the Ring Nebula, and the Cat's Eye Nebula are just a few examples of the stunning diversity that exists within these cosmic remnants. But the creation of planetary nebulae isn't just a visual marvel, it is a vital process in the recycling of the universe's material. The elements that are expelled by dying stars, elements like carbon, nitrogen, and oxygen, become the building blocks for new stars, planets, and potentially even life itself. Through the death of one star, the seeds for new cosmic creation are sown. The cycle of stellar birth and death continues, enriching the universe with the ingredients needed for future generations of stars and planets. In this way, the end of a star is not truly an end, but a transformative moment that feeds the ongoing evolution of the cosmos, pushing the boundaries of creation into the unknown. Dark matter, an elusive and invisible force, holds the key to understanding the grand dance of the universe. Though it emits no light, it plays a pivotal role in shaping the cosmos, influencing the very structure of the universe itself. While we cannot directly observe it with telescopes, dark matter's presence is inferred by its powerful gravitational influence on visible matter, radiation, and the cosmic web that stretches across the universe. Comprising roughly 27% of the total mass energy content of the universe, dark matter vastly outweighs the ordinary matter that forms the stars, planets, and even the living beings that call the universe home. The idea of dark matter first emerged in the 1930s, following an intriguing observation by Swiss astronomer Fritz Zwicky. As he examined galaxy clusters, he noticed something perplexing. The galaxies within these clusters were moving so quickly that, according to conventional gravity, they should have flown apart. There wasn't enough visible matter to hold them together, suggesting the presence of an unseen force, a hidden mass that was exerting gravitational pull beyond what was visible. Fast forward to the 1970s, and astronomers Vera Rubin and Kent Ford discovered something equally puzzling. The stars orbiting the edges of galaxies moved at the same speed as those near the galactic center, defying expectations that their speeds would slow with distance from the galactic core. These observations were groundbreaking, suggesting that there must be some unseen mass, the mysterious dark matter, exerting gravitational force and holding these galaxies together. But dark matter isn't just important for understanding the motion of galaxies. Its gravitational pull is essential for explaining the formation and evolution of the entire universe. In the earliest moments after the Big Bang, the universe was filled with tiny fluctuations in the density of matter. These fluctuations were the seeds from which all cosmic structures, stars, galaxies, and clusters would eventually form. Dark matter played a crucial role, acting like an invisible scaffolding that amplified these irregularities. By attracting ordinary matter through its gravitational pull, dark matter helped to concentrate matter in certain areas, leading to the formation of the stars and galaxies that would eventually populate the universe. Without dark matter's gravitational influence, the universe we know may never have come to be. However, dark matter doesn't only shape the past, it also has a vital role in understanding the future of the universe. Since the Big Bang, the universe has been expanding, with galaxies moving away from one another over time. Dark matter's gravity works against this expansion, slowing it down. This deceleration, however, is counterbalanced by another mysterious force: dark energy. Dark energy is an even more puzzling phenomenon than dark matter, as it drives the universe to expand at an accelerating rate. The interaction between dark matter's gravitational pull and the repulsive force of dark energy lies at the heart of the current cosmic mystery. How can the universe be held together by dark matter while simultaneously being pulled apart by dark energy? The discovery of dark energy came about in the late 1990s when astronomers observed distant supernovae and realized that the expansion of the universe wasn't merely continuing, it was accelerating. This was an unexpected revelation. According to everything known at the time, gravity should have been slowing the expansion, yet the universe was expanding faster than ever. Scientists dubbed this mysterious force dark energy, and it suggested that the very fabric of space itself was imbued with an energy that pushes galaxies apart. The nature of dark energy is one of the greatest puzzles in modern cosmology. One popular theory suggests that dark energy could be a property of space itself, as described by Albert Einstein's cosmological constant. According to this idea, empty space is not truly empty. It has its own energy that, as the universe expands and new space is created, contributes to the accelerating expansion. Another theory proposes that dark energy is a dynamic, evolving field that changes over time in space, like the electromagnetic field. In this model, the strength of dark energy could vary, potentially influencing the rate of cosmic expansion in different ways at different points in time. However, this hypothesis remains speculative, as no direct evidence for such a field has been found. As our understanding of dark matter and dark energy deepens, the fate of the universe becomes ever more uncertain. Will dark matter's gravitational pull eventually slow the expansion of the universe, or will dark energy continue to accelerate it until everything is pulled apart? The future of the universe hinges on this battle of forces, a cosmic tug-of-war that will determine its ultimate fate. And while we may not yet know how this battle will end, the mysteries of dark matter and dark energy promise to reveal even more secrets about the nature of space, time, and the very fabric of existence itself. This cosmic battle between forces of attraction and repulsion is at the heart of one of the most profound mysteries of our existence. What is the ultimate fate of the universe? For millennia, humans have looked up at the stars, pondered the vastness of the cosmos, and wondered whether the universe is a static, eternal entity, or whether it is hurtling toward a final conclusion. At the center of this mystery are the enigmatic phenomena of dark energy and dark matter, which are reshaping our understanding of the cosmos in ways that challenge everything we thought we knew. Together, these forces, along with the total mass and energy content of the universe, dictate the potential futures awaiting the vast universe we call home. One of the most pressing questions in modern cosmology is whether the universe will continue to expand forever, slowly stretching into nothingness, or if it will eventually collapse in on itself, reversing the process of its birth. At the heart of this uncertainty lies the accelerating expansion of the universe, a discovery that has shaken the foundations of cosmological theory. For most of history, it was believed that the expansion of the universe was slowing due to gravitational forces. However, current observations have unveiled a different story. The universe is not only expanding, but it is doing so at an accelerating rate. This acceleration is largely attributed to the mysterious force known as dark energy. Dark energy is a force that is both elusive and powerful, exerting a repulsive effect that counteracts the gravitational attraction of matter. It has been calculated that dark energy makes up about 68% of the universe's total energy content. This energy drives the expansion of space itself, forcing galaxies and celestial objects to drift further apart from each other. While we cannot see it, dark energy has profound implications for the future of the cosmos. The prevailing theory suggests that as dark energy continues to fuel this acceleration, the universe will expand indefinitely, growing colder and more empty over time. One particularly intriguing and somewhat somber hypothesis concerning the fate of the universe is known as the heat death scenario. This scenario draws from the laws of thermodynamics, particularly the second law, which states that entropy, essentially disorder, tends to increase over time. In the cosmic sense, this means that the universe is on a path toward a state of maximum entropy. Picture a future where energy is so evenly distributed throughout the cosmos that no distinct gradients exist to fuel processes that can do useful work. Stars will burn out, galaxies will cease forming new stars, and even black holes, those enigmatic behemoths of gravity, will slowly fade away. As black holes evaporate through a process known as Hawking radiation, they will leave behind only a sparse, diluted soup of particles scattered across an ever-expanding universe. The heat death scenario paints a bleak picture of the universe's final days. As dark energy drives the universe's expansion ever faster, matter and energy will spread thinner and thinner. Over billions of years, stars will burn through their fuel, galaxies will grow dark, and the last traces of visible activity will fade into the void. Eventually, everything will be reduced to a state of thermal equilibrium, with temperatures across the universe approaching absolute zero. No more stars will shine, no more galaxies will form, and no energy will flow to fuel any kind of process. It will be a universe without motion, change, or life. A cold, lifeless expanse where even the most fundamental forces of nature can no longer function. This scenario is based on our current understanding of physical laws, and although it sounds like the slowest of deaths, it will occur on timescales so vast they are almost incomprehensible to us, far longer than the age of the universe itself. However, not all theories about the universe's fate end in quiet stagnation. There exists another possibility, one far more dramatic and far more catastrophic, the Big Rip theory. Unlike the gradual fading of the universe in the heat death scenario, the Big Rip presents a more violent and chaotic end. At the core of this hypothesis is the role of dark energy. If dark energy continues to grow stronger over time, it could eventually overpower all the forces that currently hold the universe together. From galaxies and stars down to atoms themselves, the fabric of the cosmos could be torn apart in an unimaginable cataclysm. In the Big Rip scenario, dark energy does not remain constant, but accelerates in its power, causing the expansion of space to speed up exponentially. At first, galaxies will be torn from each other as the space between them stretches at an ever-increasing rate. As this expansion continues, the forces that bind galaxies together, gravity, electromagnetic interactions, will begin to weaken, causing galaxies to break apart. Stars will follow, their individual gravity insufficient to keep them intact. Finally, the very atoms that make up matter will be ripped apart as the expansion becomes so intense that not even the fundamental forces of nature can hold them together. The Big Rip is a chilling possibility, one that challenges the very concept of cosmic stability. The timeline leading to this end is uncertain, but it suggests a universe that, rather than fading into a cold, dark void, will explode in a final, violent rupture. It's a vision of cosmic dissolution, where everything, galaxies, stars, planets, and even atoms, will be scattered and lost in the boundless expanse. What ultimately awaits the universe? Will it fade away into nothingness, its energy slowly dissipating into an endless cold, or will it be torn apart in a cataclysmic burst of dark energy's unchecked power? Only time and the continued study of the cosmos will reveal the answers. The ultimate fate of the universe, whether gradual or catastrophic, will forever remain one of the most profound questions of science and philosophy. As the universe hurtles towards its ultimate fate, one possible scenario involves the complete disintegration of its structure. The once cohesive solar systems, including our very own, would begin to lose their binding forces. Planets, once tethered to their stars by the invisible grip of gravity, would be cast adrift, flung into the darkening void. The bonds that once held them in orbit would be severed by the relentless expansion of space, an unstoppable force powered by dark energy. In the final moments, everything we know would cease to exist in its current form. Stars, planets, and even the smallest molecules would disintegrate under the overpowering repulsive force of dark energy, which would eventually overwhelm the very forces that keep atoms bound together. As time marches on and the universe's expansion accelerates, the very atoms themselves would begin to break apart, torn asunder by the very fabric of space-time, which itself would succumb to the expanding void. The universe, once a vast network of interconnected celestial bodies, would become an empty, featureless expanse, filled with isolated particles rushing away from each other. The once grand cosmic tapestry would be no more, replaced by a cold, desolate void. This terrifyingly alien fate is known as the Big Rip, an end of the universe that hinges entirely on the mysterious nature of dark energy. If dark energy continues to grow stronger, this terrifying future is inevitable. However, if it remains constant or diminishes over time, the universe might follow an entirely different course. The potential for an eternal expansion or a reversal into contraction could lead to the universe's eventual collapse into a singularity. This collapse, known as the Big Crunch, offers another, equally staggering theory for the ultimate fate of everything we hold dear. Imagine a universe that, rather than expanding forever, gradually reverses its course. The force of gravity, which has been overpowered by dark energy's expansion for eons, would one day gain the upper hand. It would halt the outward flight of galaxies, causing them to slow, then stop, and finally reverse. In this scenario, galaxies would begin to move closer and closer, eventually colliding and merging in a cosmic dance of destruction. This process, while gradual, would be catastrophic. Over billions of years, as galaxies drew closer, they would undergo violent interactions, resulting in colossal galactic mergers. These interactions would trigger bursts of star formation, alter the structure of existing galaxies, and ultimately lead to a kind of cosmic chaos. Stars, once stable in their orbits, would collide and merge, sending shockwaves through their systems. Planetary orbits would become unstable, causing devastation on any remaining worlds. The once tranquil night sky would become an eerie, densely packed star field as the environment around these worlds turned increasingly inhospitable. As the universe contracted, the temperature and density would increase exponentially. The once stable stars and planets would be crushed together, their atoms ripped apart, until all matter was compressed into a singularity, a point of infinite density. In this scenario, the universe's end mirrors its beginning, as everything collapses into an infinitesimally small space. The pressure and temperature would reach unfathomable extremes, possibly setting the stage for another Big Bang, if the cyclic model of the universe holds true. The concept of a multiverse, however, introduces an entirely new dimension to our understanding of the cosmos. It suggests that our universe may not be alone, but part of a vast, interconnected network of universes, each with its own set of laws of physics, initial conditions, and potential fates. The fate of our universe, then, might not be as isolated as we think. In a multiverse, other universes may experience very different cosmic events. While ours might continue expanding, eventually heading toward a heat death, or the Big Rip, other universes could face entirely different outcomes, such as the Big Crunch, or scenarios that lie beyond the realm of our current scientific understanding. An intriguing twist on the multiverse theory is the idea of bubble universes. Imagine each universe as a bubble floating within a higher dimensional space. These bubbles may occasionally collide or even form through processes akin to cosmic inflation. The birth and death of these universes then become part of a much larger, more intricate cosmic framework. The fate of any one universe could be shaped by interactions with other universes, or by the specific conditions of its own birth. Within this multiverse, some universes might be entirely inhospitable to life as we know it, while others could give rise to entirely different forms of complexity and life, unimaginable in our own cosmos. In the grand cosmic theater, our universe is just one player in an immense, ever-evolving drama. Whether it ends in an eternal rip, a crushing collapse, or something entirely unforeseen, the mysteries of the universe's fate continue to captivate and baffle us, leaving us to ponder the unimaginable possibilities that lie ahead. In the vast, uncharted reaches of the cosmos, the fate of the universe remains a deeply enigmatic question, fraught with complexity and uncertainty. One theory that emerges from these uncertainties is the notion that within the multiverse, each universe might have its own unique fate. This opens the possibility that there could be as many outcomes as there are universes. In this documentary-style exploration, we delve into the myriad unknowns that influence our understanding of the universe's eventual end. The very laws of quantum mechanics, which govern the behavior of the smallest particles, add an additional layer of intrigue to the cosmos's ultimate fate. These laws introduce strange and often counterintuitive concepts like uncertainty, superposition, and entanglement, ideas that seem to defy classical notions of physics. While these principles predominantly influence microscopic particles, their potential to affect cosmic phenomena cannot be ignored. Could these quantum rules be the key to understanding the universe's destiny? Perhaps one of the most fascinating intersections of quantum mechanics and cosmology lies in the realm of black holes. Stephen Hawking's groundbreaking theory of Hawking radiation suggests that black holes, those seemingly infinite voids, might not be as permanent as once thought. Over eons, black holes could emit radiation and slowly evaporate, potentially altering the universe's long-term trajectory. This slow decay through quantum processes might be one of the last great cosmic events in a dying universe. As black holes eventually vanish, their energy could fuel the final remnants of the universe's evolution, playing a critical role in scenarios like the heat death of the cosmos. Yet, this evaporation of black holes is only one facet of quantum mechanics' possible impact on the universe's future. The concept of quantum fluctuations, temporary changes in the energy of space, may hold the key to understanding the birth of cosmic structures like galaxies. Early quantum fluctuations were integral in shaping the large structures we observe today. Looking ahead, it is conceivable that similar fluctuations could give rise to new particles or even entire universes. The idea of false vacuum decay, where quantum transitions might stabilize a more permanent vacuum state, suggests that the universe could evolve in ways that defy our current understanding. The emergence of new universes within a multiverse framework could radically reshape the fate of all that exists. Moreover, quantum mechanics challenges our fundamental understanding of time and causality, two concepts traditionally at the heart of cosmological discussions. Quantum entanglement, the phenomenon where particles become instantaneously linked regardless of distance, suggests that cause and effect may not operate in the straightforward linear manner we have long assumed. Instead, this interconnectedness could imply that the universe's fate involves complex, non-local interactions. The universe's end may not be a singular, predictable event, but a process influenced by mysterious forces yet to be fully understood. As we look to the future, quantum cosmology presents tantalizing possibilities about the origin and destiny of the universe. This field applies the principles of quantum mechanics to the entire cosmos, suggesting that the universe itself might have emerged from nothing via quantum fluctuations. This theory opens the door to models of cyclic or bouncing universes, where the death of one universe could give rise to another, each one born from the quantum vacuum of its predecessor. Such theories offer exciting prospects for the multiverse, where our own universe could be only one in an infinite series of cosmic rebirths. Yet, even with these groundbreaking ideas, much about the universe remains cloaked in mystery. In our quest to understand the cosmos, we have uncovered some of its most profound secrets, from the laws of gravity that bind galaxies to the strange workings of subatomic particles. However, there is still so much more to learn. The history of science is full of moments when new forces or phenomena radically reshaped our understanding of reality. Could we be on the verge of another such revelation? One of the most tantalizing mysteries lies in the dark sector, the unknown forces that make up the vast majority of the universe's mass energy content. Dark matter and dark energy, though invisible and enigmatic, wield an undeniable influence on the cosmos. As scientists continue to study these elusive entities, we may uncover entirely new properties or even identify entirely new forms of dark matter. Such a discovery could drastically alter our predictions for the universe's ultimate fate. Furthermore, the search for a unified theory of everything, a framework that merges quantum mechanics with general relativity, promises to shed light on deeper cosmic truths. Theoretical models like string theory and loop quantum gravity suggest that additional dimensions or undiscovered fundamental particles may exist, potentially explaining phenomena that our current models cannot. These breakthroughs could radically change our understanding of the universe's evolution, offering new insights into its eventual demise. In addition to these theoretical constructs, scientists continue to investigate cosmic anomalies, unexpected observations that challenge our existing models. Discrepancies in the velocities of galaxies within clusters and in the outer regions of galaxies were among the first clues pointing to the existence of dark matter. Future anomalies may provide the key to uncovering new forces or constituents that could shape the future of the universe. Even the very beginning of the universe remains a mystery. The first moments after the Big Bang during cosmic inflation were shrouded in uncertainty, and phenomena at those energy scales may have left traces that we have yet to detect or fully interpret. These imprints could hold the answers to questions we haven't even thought to ask yet, providing clues to the forces that have shaped the universe's past and will ultimately determine its future. As we continue to explore the cosmos, the universe's fate remains as uncertain as ever. With every discovery, we inch closer to understanding the fundamental forces that govern reality. Yet, the vastness of the unknown continues to remind us of the limits of our knowledge, urging us to keep asking questions and exploring the mysteries that lie beyond the stars. The notion that humanity could shape the fate of the universe is both audacious and profound. It merges the vast mysteries of cosmology with the boundless creativity of human ingenuity, urging us to rethink our place in the grand cosmic narrative. While the universe dwarfs human ambition in both size and power, the accelerating pace of technological development and our ever-expanding understanding of the cosmos prompt a thrilling possibility. Could intelligent life influence the very structure of the universe itself? Humankind's mastery over our environment has already transformed Earth in ways once thought impossible. From engineering the land to developing intricate technologies that alter the planet's course, we have demonstrated our ability to change our surroundings. Yet, our ventures into space, though still in their infancy, are the first tentative steps towards something far grander. As we push beyond the confines of Earth, we start to entertain the idea that we might one day influence forces far larger than ourselves. Take the concept of the Dyson sphere, a hypothetical megastructure designed to encapsulate a star, capturing its energy to power an advanced civilization. While such an idea currently lies far beyond our technological grasp, it serves as a fascinating glimpse into what could be possible. A Dyson sphere represents a significant leap, enabling civilizations to harvest stellar energy directly and exert control over the forces of nature. This is just one example of how humanity could harness the raw power of the cosmos, illustrating that we may one day hold the tools to shape space environments. And yet this is only the beginning. The search for a unified theory of physics, one that merges all fundamental forces into a single framework, might be the key to unlocking even more extraordinary possibilities. Imagine a future where we can manipulate gravity, alter the very fabric of space-time, or even create artificial black holes. With such advances, humanity could stabilize star systems, prevent the catastrophic collapse of celestial bodies, or even engineer entire galaxies to our will. In this speculative future, the scope of our influence could extend beyond mere stellar manipulation. Humanity might become the driving force behind the spread of life itself. Consider the theory of directed panspermia, where intelligent beings intentionally distribute life across the universe, seeding other planets with the potential for life. In such a future, humans could become the architects of new worlds, guiding the development of life in distant star systems, and possibly even fostering the rise of other intelligent species. In this sense, we would not only be stewards of our own world, but also of entire galaxies, influencing the course of evolution across the cosmos. However, for humanity to truly shape the universe, we would need to overcome immense challenges. The vast distances between stars, the inhospitable nature of space, and the creation of sustainable off-Earth habitats are just a few of the obstacles we must confront. Achieving such monumental feats would demand not just groundbreaking technology, but also unwavering cooperation and a deep sense of responsibility toward the resources and wonders of the cosmos. While the current scale of the universe may make humanity's impact seem insignificant, the potential for growth in both knowledge and technological prowess suggests that we should not underestimate the role of intelligent life in shaping cosmic events. Over time, our abilities may grow to the point where we can influence the universe on a grand scale, whether by manipulating cosmic phenomena, guiding the spread of life, or reshaping our relationship with the stars themselves. In this way, humanity could introduce a dynamic, living element into the fabric of the cosmos. As we contemplate the ultimate fate of the universe, we must consider the concept of entropy, the measure of disorder that governs all systems. According to the second law of thermodynamics, entropy always increases over time, pushing systems toward a state of maximum disorder. For the universe, this means an inevitable path toward heat death, or maximum entropy, where all energy is evenly distributed and temperature gradients cease to exist. In this state, no work can be done, as the very foundation of work is energy movement from high to low concentrations. This concept, while daunting, may provide us with a glimpse into the universe's final destiny. Yet, even as entropy seems to promise an inevitable end, it also prompts the question, what role could humanity play in this cosmic finality? Could we, through advanced technologies and understanding, intervene in the universe's march toward entropy, staving off or even reversing its effects? As we venture further into the unknown, the possibility that we might one day influence the ultimate end of the universe becomes ever more tantalizing. Through the convergence of technology, ingenuity, and cosmic understanding, humanity could play a pivotal role in shaping not only its own future, but the very structure of the universe itself. While the cosmos may seem vast and beyond our control, the potential for human influence grows ever clearer, inviting us to reimagine our relationship with the stars and our destiny in the grand expanse of space. In the distant future, a profound transformation will sweep through the cosmos, ushering in an era where the very nature of the universe as we know it will be radically altered. The processes that once fueled the dynamic activities of life, stars and galaxies, will slowly grind to a halt. The once thriving universe, alive with energy, will collapse into a state of cosmic stillness. Energy-consuming phenomena, such as the formation of stars, the brilliance of stellar explosions, the forging of planets, and even the decay of black holes, will cease. Instead of the vibrant, ever-evolving cosmos we observe today, a stagnant and featureless expanse will dominate. The universe at this point will have reached a state of thermal equilibrium, a condition in which all regions of space are at the same temperature and no gradients remain to fuel movement or the creation of new structures. It is a universe devoid of life, of stars, of planets, indeed, even of galaxies. These once energetic celestial bodies would have long since exhausted their nuclear fuel, with no new stars born to replace the old. Black holes, those enigmatic remnants of collapsed stars and the central engines of galaxies, will be the final cosmic structures to undergo a slow, inevitable decay. Through Hawking radiation, predicted by physicist Stephen Hawking, black holes will gradually lose their mass and energy. Hawking radiation arises due to quantum fluctuations near the event horizon of black holes, where particle-antiparticle pairs spontaneously appear. While one of these particles may fall into the black hole, the other escapes into space, causing the black hole to lose energy. Over unimaginable periods of time, these small emissions gradually erode the black hole's mass. For large black holes, this process is incredibly slow, taking an incomprehensible number of years, far longer than the current age of the universe. But eventually, as the universe expands and ages, these black holes will stand as the only remaining beacons in an otherwise quiet and cooling cosmos. As the black holes lose mass, they will eventually evaporate entirely, and with this evaporation, they will release their energy into the universe. But this energy will no longer create the cosmic phenomena that once gave the universe its structure and vitality. Instead, it will spread across an increasingly sparse and ever-expanding space. The gradual release of this energy, no longer concentrated in large celestial bodies, marks the universe's inexorable journey toward maximum entropy. In this state, energy will be spread thinly and evenly, and no significant concentrations of mass or energy will remain to form new stars or galaxies. The black holes, once the titanic remnants of the universe's most violent and dynamic events, will fade into oblivion, leaving behind only low-energy particles, photons, electrons, neutrinos, and perhaps dark matter, in a universe where nothing is left to drive movement or change. The final act of this cosmic drama, the evaporation of the last black hole, will signify the universe's final transition to an unchanging state. This event could take up to 10 to 100 years to unfold, a span so vast it dwarfs our current understanding of time. The end result will be a universe where nothing but an even distribution of radiation and fundamental particles exists, a universe devoid of the high-energy events that once shaped its history. It will be a quiet, desolate cosmos, far removed from the vibrant, chaotic universe that gave birth to life as we know it. Yet, amid this bleak and irreversible cooling of the universe, there may still be the tiniest glimmer of possibility. Life, as we understand it, might struggle to survive in such an environment, but that doesn't mean the end of all forms of existence. Theoretical speculations have suggested that if any form of consciousness or life is to endure into this distant future, it would require extreme adaptation. New forms of technology, biology, and energy utilization would be necessary to withstand the immense challenges posed by such a barren universe. Life could potentially harness the energy released by the last remnants of black holes, tapping into the Hawking radiation emitted as they evaporate. These hypothetical civilizations would need to be able to extract energy from the thinnest of resources, including the radiation that pervades space or even directly converting mass into energy. The potential for survival, however, would depend on breakthroughs in technologies far beyond anything we currently comprehend. This might even involve the development of completely new forms of life or energy systems that can exist in a universe where traditional energy sources like sunlight or chemical reactions are no longer viable. In such a universe, the struggle for survival would not just be about adapting to a new environment, but understanding the very laws of physics in a radically different context, one where the universe's entropy has reached its peak and is spread too thin to drive meaningful processes. For the few that might adapt, it would be a testament to the astonishing resilience of life, an endurance that defies the ultimate cold, quiet fate of the cosmos. In this distant future, the universe will no longer be the place of stars and galaxies. It will become a vast, cold expanse, one where the only legacy of life might be in the minds of those who imagined it against the backdrop of a dying universe. As the universe continues to expand, matter becomes increasingly sparse, and the vast emptiness stretches further into the unknown. Yet, even in this cold, desolate future, there may still be ways for life to persist. One possibility lies in the ability to extract usable energy from the few remaining particles and radiation. This could require radically advanced technology, perhaps even new forms of matter manipulation or quantum-level mechanisms designed to harness the energy from subatomic particles themselves. In such a scenario, the very nature of life would need to adapt, Organisms that once thrived in environments rich with energy might need to evolve or be bioengineered to survive on much less. These new life forms could be low-energy entities designed to endure in a universe with almost no resources. They might have the ability to hibernate for millennia, awakening only when energy becomes available, or function with reduced metabolic activity, allowing them to live for eons with minimal sustenance. The demands of such a universe would likely require a level of autonomy beyond what we can currently imagine. The isolation imposed by the vast distances between any remaining energy sources means that any surviving life forms would need to be self-sufficient. These entities would have to repair themselves, replicate and adapt without the need for external input, creating the possibility of completely new types of life or consciousness. Such beings might not even be biological, but instead could be based on new technologies, perhaps structures based on quantum computing, which could operate on a level of efficiency far beyond our understanding. In these dark times, survival would also depend on the ability to communicate across immense distances. Travel between distant regions of the universe, where energy might still be found, would be incredibly difficult, if not impossible. Instead, surviving entities might develop highly sophisticated forms of information storage and transmission. Knowledge itself could become the most valuable currency, preserved and passed on through generations in an effort to maintain society, even if that society exists in a vastly different form than we know today. As the universe marches ever closer to its ultimate fate, whether it be through heat death, the Big Rip, or another theory, the very fabric of time and causality could be radically altered. Time, as we experience it, is inextricably linked to the second law of thermodynamics, the idea that entropy or disorder always increases in a closed system. As the universe winds down, with fewer events to mark the passage of time, this flow could become indistinguishable. Without any significant changes in energy states, entities may lose any sense of time altogether. This raises deep philosophical questions about the very nature of time itself. Is it a fundamental property of the universe, or is it merely an emergent concept, something that only exists because of the continual cycle of cause and effect? In a universe that is slowly winding down, the concept of causality, the relationship between cause and effect, might also be in question. Quantum mechanics already challenges our classical understanding of causality, with phenomena like entanglement, where particles appear to communicate instantly, no matter how far apart they are. As we push our understanding of the universe's fate, we may discover that the laws governing spacetime and causality operate in ways that challenge everything we know. Speculative theories, such as the cyclic model of the universe, where the cosmos expands and contracts endlessly, or the existence of a multiverse, could add yet another layer of complexity to our understanding of time. In such models, time might no longer be a linear progression from a single beginning to an eventual end, but instead a multidimensional landscape, where the rules of causality behave in ways that are currently unimaginable. If life were to survive in such a universe, the very way that those entities perceive and interact with time could evolve. They might develop entirely new frameworks for understanding the passage of time, frameworks that account for the extreme conditions of a maximally entropic universe, or that integrate quantum mechanical insights into a broader cosmological theory. These new frameworks could challenge our basic assumptions about time and causality, reshaping our understanding of reality itself. Even as the universe moves towards its final stages, where energy and matter are but faint remnants of their former selves, quantum fluctuations might remain. These temporary changes in energy that occur in an otherwise empty vacuum reveal the unpredictable nature of quantum mechanics. In such an environment, where the universe seems to slow to a crawl, the seemingly chaotic energy fluctuations could be one of the last remaining sources of life and progress. In the end, the survival of life in a dying universe may hinge on our ability to adapt not just our biology, but our understanding of the fundamental forces that shape our reality. Through radical technological and biological evolution, life might find a way to endure long after the stars have burned out. Yet, whether time itself remains a constant or becomes a relic of a bygone era remains one of the greatest mysteries of the cosmos. In a universe nearing its end, one that is on the verge of or has already reached maximum entropy, where the stars have burned out, the galaxies have dispersed, and absolute cold has descended, there still lies a flicker of possibility. Even in the face of such an unimaginable stillness, a strange and remarkable phenomenon might emerge: quantum fluctuations. These fluctuations, though seemingly trivial, could be the key to unlocking the very fabric of our existence, and perhaps the cosmos itself. Theoretical physicists have long speculated that under the right conditions, these quantum fluctuations could spark the birth of entirely new universes. This idea is more than a mere speculation. It suggests a potential cyclical nature of the cosmos, where the death of one universe gives rise to the birth of another. In a universe where matter is almost entirely devoid and energy is evenly distributed, one might expect a complete stasis. However, the very foundation of spacetime, even at its most seemingly lifeless, could continue to experience quantum fluctuations, tiny, brief distortions in the fabric of reality itself. These fluctuations, although barely perceptible in everyday life, have the potential to give birth to virtual particles, brief bursts of energy that exist momentarily before vanishing. It's a process we have already observed in laboratory experiments, but the implications of these fluctuations extend far beyond our current understanding. Under extremely rare and precise conditions, one of these fluctuations could become more than just a temporary blip in spacetime. Imagine, if you will, that a quantum fluctuation might generate a concentration of energy so intense, so dense, that it could trigger a chain reaction, a new Big Bang. This would mark the birth of an entirely new universe, nested within the dying remnants of its predecessor. It's a mind-boggling notion that pushes the boundaries of our understanding of reality, but it also opens up fascinating possibilities for the existence of a multiverse, an ensemble of multiple universes, each with its own set of physical laws, constants, and perhaps even entirely different forms of matter and energy. In such a framework, every death of a universe could be a prelude to the birth of another, suggesting that the cosmos itself is in an eternal state of rebirth. Time, causality, and the very essence of existence would need to be redefined in such a universe, where the end of one cosmic era is simply the beginning of another. This idea of an eternal and cyclical universe, where each death births a new life, stands in stark contrast to the traditional view of cosmology. The linear model, from the Big Bang to the ultimate heat death of the universe, seems increasingly inadequate to explain the true nature of reality. But what if the singularities that lie within the heart of black holes are not simply endpoints for the matter that enters them? What if they are instead the very seeds of new universes, waiting to burst forth and create entirely new realms of existence? A singularity, the point at the center of a black hole where matter collapses to infinite density, is one of the most enigmatic phenomena in the cosmos. It is a place where the laws of physics, as we know them, break down, and the very fabric of spacetime is twisted beyond recognition. But what if these singularities, rather than marking the final chapter of a universe's story, serve as the beginning of a new one? This is the tantalizing hypothesis that some cosmologists are now exploring, that the extreme gravitational forces within a black hole could rupture spacetime itself, creating a bridge, a wormhole, to another region of the universe, or even an entirely new universe that emerges from the black hole's depths. This idea shifts our perception of black holes from being the cosmic graveyards of stars to being potential gateways to new universes, where the birth of one cosmos is intimately tied to the death of another. The notion that black holes could give birth to new universes challenges our conventional understanding of causality and the flow of time. If a singularity can be a point of creation as well as destruction, the very foundation of how we understand the universe's life cycle must be reimagined. The birth of a new universe from the heart of a black hole would imply that the end of one cosmic epoch is inherently linked to the beginning of another. This creates a model for the multiverse, where every black hole acts as a potential birth canal for a new cosmos, growing the multiverse with each cycle of life and death. Such a view of black holes radically transforms how we see them. They are no longer just the final resting places for dying stars, but rather the origins of entirely new universes, places where the cycle of creation continues unbroken. This perspective fits neatly with the broader cosmological view that the universe is dynamic and ever-changing, with processes at both the grandest and most microscopic scales contributing to its ongoing evolution. If the multiverse theory proves correct, and our universe is just one of many with different physical laws, constants, and perhaps even alternate realities, the implications stretch far beyond just the cosmos itself. It raises profound questions about consciousness and information. What happens to them once our universe has run its course? Could information persist beyond the life of a single universe, traveling across the multiverse, perhaps even transcending space and time as we know them? This vision of an endlessly reborn cosmos, an eternal cycle of creation, destruction, and recreation, adds a new layer of mystery to the age-old questions of existence. The possibility that each universe is part of an ever-expanding multiverse, generated by the quantum fluctuations and singularities within black holes, invites us to rethink everything we thought we knew about the universe and our place within it. As the universe marches towards its inevitable end, the intriguing possibility arises: could consciousness or information escape its clutches and find refuge in another universe? This speculative idea sits at the intersection of cosmology, quantum mechanics, and the theories surrounding the mind and the nature of information itself. But how could such a miraculous transfer occur? What hidden pathways might allow the essence of our universe, including consciousness, to survive beyond the death of the cosmos? The answers, though far from certain, may lie in the very fabric of quantum entanglement and the mysterious depths of black holes. Quantum entanglement is a phenomenon that defies our conventional understanding of physics. When particles become entangled, their states become intertwined so that the state of one particle can instantaneously affect the state of the other, even if they are separated by vast distances. This strange connection leads some theorists to propose that if all information within our universe, every bit of data, including the states of consciousness, could somehow be entangled with particles in another universe, there might be a way for the information to transcend the boundaries of its home universe. Such a transfer would be free from the constraints of space and time, existing outside the conventional limits of death that govern our universe's fate. But how could we even begin to conceptualize this? A more tangible possibility lies in the singularities of black holes, those incredibly dense regions of space where the gravitational pull is so intense that not even light can escape. Some theories suggest that black holes may act as portals or wormholes, connecting different regions of space-time and potentially even different universes. If consciousness or information could be encoded in a way that survives the harrowing journey through such a singularity, it could provide a lifeline to another universe, one untouched by the decay of the current cosmos. However, this concept requires us to drastically rethink our understanding of consciousness itself. What if consciousness is not merely a product of the biological brain, but a deeper, more fundamental force capable of existing independently of any physical substrate? This question introduces the fascinating idea of digital consciousness. What if our minds could be uploaded, replicated on a non-biological platform, and then transported across the void between universes? Such a leap would require not only an understanding of how to digitize consciousness, but also the ability to withstand the extreme conditions that would accompany such an inter-universal journey. Yet, despite the allure of these speculative pathways, each one faces monumental scientific and philosophical hurdles. Quantum entanglement, though proven in experiments, does not yet provide a practical means of transferring complex information, let alone something as intricate as consciousness. The notion of black holes acting as bridges to other universes is grounded in theory, with no concrete evidence to support the idea that singularities can connect to realms beyond our own. Moreover, the very concept of transferring consciousness presupposes that we could fully understand and replicate it outside its biological context, an idea that challenges our deepest understanding of identity, selfhood, and the continuity of experience. As we contemplate the future of the universe, the conservation of information stands as a cornerstone of quantum theory. According to this principle, information, no matter how transformed or obscured, cannot be destroyed. This concept raises profound questions about the universe's ultimate fate. If information cannot be annihilated, does that imply that as the universe reaches the brink of its death, all its information, its history, its structure, even the essence of life and consciousness might be preserved in some form? Could this preserved information serve as the foundation for a cosmic rebirth, enabling the universe to regenerate in some way, much like the mythical phoenix rising from its ashes? One of the most thought-provoking challenges to our understanding of information comes from the black hole information paradox. Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation, and can eventually evaporate, contradicts the previous belief that information entering a black hole is lost forever. The paradox is striking. If a black hole evaporates and vanishes, what happens to the information it once contained? The conservation of information principle insists that this information must be preserved, and some have suggested that it could be encoded within the Hawking radiation itself. This theory leads to deeper questions about the nature of information at the quantum level and the very nature of reality itself. If we take this a step further, one bold theory proposes that at the end of time, all the information about our universe might be encoded on a two-dimensional surface at the universe's boundary, adhering to the holographic principle, which asserts that all the information of a volume can be encoded on its boundary. Such a model could have profound implications for the universe's final moments. Imagine, as the universe collapses in on itself, all the data, everything that has ever happened, every star that has ever burned, every consciousness that has ever existed, being preserved on this cosmic boundary. This preserved information could serve as a template for the universe's rebirth, a potential blueprint for the next cycle of existence. If the universe is indeed cyclic, constantly dying and being reborn, then the information we hold dear, our very essence, could persist in some form, waiting to re-emerge in the next iteration of existence. These questions, though speculative, force us to confront some of the deepest mysteries of existence. They challenge our very understanding of life, death, and consciousness, and open the door to possibilities that lie far beyond the limits of current scientific knowledge. Could our minds transcend the death of the universe? Could we escape to another realm where life continues in a new form? As the universe edges toward its ultimate fate, these questions remain unanswered, but they are questions that may one day define the future of existence itself. As we gaze into the depths of space and unravel the mysteries of the cosmos, we are often confronted with a profound question. Is the universe truly eternal, or is it part of an endless cycle of birth, death, and rebirth? Imagine for a moment that the universe follows a cyclical pattern, one where each grand cycle, marked by the cataclysmic events of a Big Bang and the inevitable contraction of a Big Crunch, shapes the next. If such a model holds true, then the universe we live in today may not be a blank slate, but rather a continuation of its predecessor, carrying with it echoes of what came before. These echoes are not merely the remnants of matter or energy. They are the very information embedded in the fabric of the universe, conserved through the enigmatic laws of quantum mechanics. In this hypothetical scenario, each cosmic cycle is not a singular, isolated event, but a thread in an infinite tapestry, where the information preserved at the end of one universe influences the birth of the next. Through advancements in our understanding of quantum gravity, which seeks to merge the vast and powerful framework of general relativity with the subtle intricacies of quantum mechanics, we could uncover how information is retained even as the universe meets its demise. This retained information might not simply dissipate into nothingness, but could instead lay the groundwork for the formation of new universes, carrying with it imprints from the past that shape the very geometry of space and the distribution of matter in the next universe. Such a realization suggests a cosmos where the end and the beginning are not opposing forces, but are intrinsically connected, linked by the immutable principle of information conservation. As we contemplate the vastness of the cosmos and the possibility that each cycle carries forward the seeds of the next, our understanding of the universe's end and its rebirth takes on new meaning. But what does this grand cosmic dance mean for us, humanity, existing on this tiny blue dot, teeming with life, yet fleeting in time? At first glance, the scope of the universe's fate might seem to dwarf our significance, reminding us of our infinitesimal place in the grand scheme of things. However, rather than diminishing our importance, this realization can elevate our appreciation for the complexities and beauty of the universe. The very fact that we are able to comprehend the universe's mysteries, no matter how small our presence may seem, adds value to our existence. This humbling perspective, this awareness of our smallness, becomes a source of inspiration rather than despair. Such a realization brings with it a sense of cosmic humility. We begin to understand that our lives, our civilizations, and even our planet exist within a much larger, older process that stretches far beyond our immediate concerns. In this vast, ever-evolving cosmic web, we are mere transient inhabitants. This cosmic humility challenges us to reevaluate our place within the universe and reframe our existential questions. Rather than fixating solely on our human-centered narrative, we are invited to expand our perspective, to consider the possibility that our lives are part of a much broader, cyclical existence. Perhaps in this grand cosmic cycle, the legacy of humanity and life itself is encoded within the universe's very structure, leaving behind a trace that transcends our earthly existence. But the implications of understanding the universe's cyclical nature go beyond philosophical reflection. They directly influence how we approach our daily lives, the care we take in preserving our planet, and the legacy we wish to leave behind. If we truly understand the rarity and preciousness of life, set against the backdrop of an impermanent universe, it becomes clear that we have a responsibility not only to ourselves, but also to future generations. The knowledge that life as we know it is fragile, that our planet's conditions are unique and precious, could fuel efforts to pursue sustainable living, promote the preservation of biodiversity, and advocate for interstellar exploration. These goals, once thought to be distant ambitions, become more urgent when we consider the possibility of an eventual cosmic end. Humanity's creativity, its pursuit of knowledge, and its endeavors in science and technology could serve as our response to the impermanence of the universe. This awareness, though sobering, can spark profound creativity. The thought of an end, whether to a single life, a species, or the entire universe, has inspired countless works of art, literature, music, and scientific breakthroughs. In contemplating the universe's demise, artists, thinkers, and creators have long wrestled with impermanence, weaving themes of loss, renewal, and the eternal cycle into their work. The mystery and vastness of the cosmos, coupled with its eventual end, serve as a muse that sparks creativity and introspection. For scientists, this contemplation pushes the boundaries of inquiry, urging them to reach beyond current limits, to explore the stars, to uncover the fundamental laws of nature, and to explore the possibility of transcending not just our earthly origins, but perhaps even the lifespan of the universe itself. On a philosophical level, the end of the universe challenges us to rethink our values, our ethics, and our responsibilities. It forces us to confront the finiteness of our existence, not just as individuals, but as a species. The knowledge that everything we know is ultimately transient prompts us to find meaning in the fleeting moments we experience. It encourages us to invest in the legacy we leave behind, to cherish the beauty of life, and to cultivate a deeper understanding of the interconnectedness of all things. In this light, we come to appreciate the fragility of our existence, and rather than surrendering to despair, we are inspired to live with greater intention, purpose, and love. Finally, as we face the inevitability of the universe's end, we are confronted with the urgency to create meaning. In a universe that is not eternal, where all things will eventually fade, it is the choices we make, the connections we forge, and the beauty we create that give our lives meaning. This realization, far from rendering us helpless, empowers us to live fully and with intention, to embrace the preciousness of each moment, and to leave a lasting impact on the world and the people we love. This awareness has the potential to spark a fundamental shift in human perspective, one that moves away from the pursuit of fleeting external validation and towards the cultivation of an inner richness that can truly withstand the test of time. It encourages us to move beyond the accumulation of material wealth, urging us instead to focus on enriching the world, leaving behind contributions that could echo through the ages, impacting generations to come. In this moment of reflection, humanity stands on the precipice of a transformative challenge, one that pushes the boundaries of imagination and reaches into the realm of the unknown. Contemplating the preservation of knowledge across eons, we embark on an endeavor unlike any other, a mission to ensure that the legacy of our existence endures beyond the limits of our time. This vision involves passing down our collective wisdom, understanding, and experiences to potential future civilizations or intelligences that might arise, whether here on Earth or in far-flung corners of the universe. However, this monumental task is fraught with challenges that not only demand ingenuity, but also a rethinking of how we approach the very essence of communication itself. The preservation of information is not a simple matter. It requires safeguarding our knowledge in a way that can withstand not only the ravages of time, but also the unpredictable nature of cosmic events, such as solar flares, asteroid impacts, and the eventual death of stars. To accomplish this, we must think beyond the conventional boundaries of time, considering methods that could transcend the limitations of current technologies and languages. We must devise messages and mediums that could communicate with entities whose experiences, perceptions, and technologies may be radically different from our own. One approach to this challenge involves creating durable time capsules or monuments, capable of withstanding the relentless forces of nature and time. These could take the form of plaques, sculptures, or other enduring structures made from materials resilient to erosion, corrosion, and the harshness of cosmic radiation. Substances like platinum or silicon carbide, capable of withstanding the test of millennia or even billions of years. A prime example of such an effort is the Voyager Golden Records, which, even as they journey into the far reaches of space aboard the Voyager spacecraft, contain a rich representation of Earth's diverse cultures, sounds, and images, serving as a potential message to any intelligence that might someday come across them. In addition to physical monuments, we now turn to more innovative methods of information, one of the most promising being the encoding of data in DNA. The compactness and longevity of DNA make it an ideal candidate for storing vast amounts of information, far surpassing anything possible with traditional digital storage. Scientists have already begun experimenting with encoding digital data in DNA strands, a technique that could one day serve as a means of archiving the history, science, culture, and technology of humanity. Imagine DNA-based archives dispersed across the planet or even into space, safeguarded within protective capsules, awaiting discovery by future beings, whether they be our descendants or alien life forms with technologies beyond our comprehension. Yet the medium alone is not enough. The messages we choose to preserve must be crafted with universal principles in mind, transcending the limitations of human language and culture. These communications must reflect fundamental truths that any intelligent being, regardless of origin or technology, can understand. Mathematical sequences, universal constants like the speed of light, and pictograms depicting human anatomy or the location of Earth in relation to known celestial bodies could form the basis of such messages. One notable attempt at this type of communication was the Arecibo message, transmitted into space in 1974, which used binary code to convey basic information about humanity and our solar system. Beyond these physical and technological methods, humanity may eventually turn to more speculative avenues, such as quantum entanglement, a phenomenon on the cutting edge of our understanding of physics. While still deeply theoretical, these concepts open the door to an entirely new realm of possibilities, where information could potentially be sent across time, bypassing the need for traditional media entirely. These ideas may sound like the stuff of science fiction, but they reflect the boundless creativity and ambition with which we approach this cosmic challenge. Furthermore, there is the question of preserving knowledge not just for future generations, but within our very own civilization. Creating and maintaining repositories of knowledge, whether physical or digital, dedicated to safeguarding information for posterity, is a crucial step in this endeavor. These archives would not merely store data, but also include vital instructions for interpreting and understanding that information, decoding human languages, technologies, and cultural contexts that may no longer be understood in the distant future. These repositories would serve as the bridges between the present and the future, ensuring that our knowledge is not lost, but instead remains accessible and understandable for centuries to come. As humanity continues its journey of exploration, both outward into the cosmos and inward into the mysteries of the universe, we are confronted with a deeper awareness of our place in the grand tapestry of existence. The awareness of our mortality and the eventual fate of our planet raises profound ethical questions, ones that extend far beyond our immediate concerns. How should we interact with the universe, knowing that it will one day cease to exist in its current form? What responsibilities do we bear toward future generations and potential extraterrestrial civilizations? And how should we conduct ourselves, knowing that our actions today may echo across the cosmos for eons? The choices we make now, guided by this newfound awareness, are not just about preserving knowledge or securing a legacy. They carry far-reaching implications, not only for humanity, but for the entire universe. Our stewardship of this knowledge and our efforts to ensure that it endures may well define the very essence of our legacy, touching the future in ways we can only begin to comprehend. It is in these reflections, contemplating the vastness of the cosmos and the fragility of our existence, that we find the true depth of our responsibility as custodians of the knowledge we pass on to the future. As we delve deeper into the vastness of the cosmos, the ethical engagement with the universe becomes an indispensable principle. A profound respect for the cosmos is not simply a philosophical ideal, but a fundamental necessity for the continuation of human life and exploration. This respect is manifested in the urgent need for cosmic preservation and a conscious commitment to avoid actions that might disrupt the delicate balance of celestial environments. It is no longer just about exploring space for the sake of discovery, but also about safeguarding the pristine nature of these environments. As humanity ventures beyond our home planet, the ethics of non-contamination and the preservation of celestial bodies in their natural states become paramount. These guidelines are more than just a matter of scientific integrity. They are a direct reflection of our reverence for the universe itself. They ensure that the knowledge we gather remains pure, untarnished by human interference, and that the intrinsic value of these celestial bodies remains intact for future generations. By respecting the universe as a whole, we affirm the belief that its worth extends far beyond any potential utility to humankind. Building upon this, our understanding of the universe's eventual fate underscores a responsibility that stretches far beyond the present moment. The ethical imperative that we pass on a legacy of knowledge and curiosity to future generations is a call to action for all of humanity. This responsibility includes not only ensuring that future explorers inherit a deep well of scientific understanding, but also equipping them with the tools and technologies necessary to navigate a changing universe. As we unlock the mysteries of the cosmos, we also open new frontiers that could one day offer humanity new homes beyond Earth. The need to invest in long-term sustainability and interstellar exploration is more than a technological pursuit. It is a commitment to the preservation of life itself, both human and terrestrial. This commitment becomes a profound testament to our desire to ensure the continuity of life in an ever-evolving universe. The ethical dilemmas that arise from the potential discovery of extraterrestrial life raise even more complex questions. How should we communicate? What is the right way to coexist with intelligent beings that may not share our values or even our biology? In this new age of cosmic exploration, the principles of mutual respect, non-interference, and peaceful cooperation must guide our approach. The discovery of extraterrestrial life would not simply challenge our scientific understanding, but also compel us to reevaluate our moral responsibilities on a universal scale. Engaging with alien civilizations requires the recognition of their autonomy and rights, and it is through these interactions that humanity can showcase its commitment to ethical conduct, both on Earth and across the cosmos. Our approach to these encounters, grounded in respect and understanding, will define not just our future in space, but the legacy we leave in the universe. In this vast journey to uncover the mysteries of the cosmos, we rely on powerful instruments like the Hubble Space Telescope and the James Webb Space Telescope, which serve as humanity's windows into the universe. These instruments, more than mere telescopes, are the very keys to unlocking the secrets of space, providing us with the ability to peer into the universe's past and future. The Hubble Space Telescope, launched in 1990, has long been at the forefront of cosmic exploration, offering groundbreaking insights into the universe's expansion, the formation of galaxies, and the enigmatic force of dark energy. Through its advanced imaging capabilities, Hubble has revealed wonders such as the Hubble Deep Field images, where thousands of galaxies were captured in a single image of what was once thought to be empty space. These images have not only expanded our understanding of the universe's size, but have also helped refine our estimates of its age and the rate at which it is expanding. The discovery of dark energy, a mysterious force driving the acceleration of this expansion, was another monumental breakthrough made possible by Hubble's observations. However, it is the James Webb Space Telescope, JWST, launched in December 2021, that represents the next frontier of space observation. While Hubble has provided invaluable data in visible and ultraviolet light, the JWST's focus on infrared wavelengths allows it to peer through the cosmic dust that often obscures our view of distant galaxies and stars. The JWST can observe light emitted by the very first galaxies that formed after the Big Bang, giving us an unprecedented glimpse into the origins of the universe. This capability is crucial not only for understanding the formation of galaxies, stars, and planetary systems, but also for investigating the potential for life beyond Earth. The JWST's ability to look deeper into space and further back in time marks a new chapter in our quest for answers about the origins of life and the conditions that might sustain it elsewhere in the cosmos. Both the Hubble and James Webb telescopes play crucial roles in uncovering the ultimate fate of the universe. By studying the rate of cosmic expansion and observing distant supernovae, scientists have gathered evidence pointing to the accelerating expansion of the universe, a discovery that challenges existing theories and compels new models of cosmological evolution. These telescopes are also instrumental in tracking the life cycle of stars, from their birth in nebulae to their dramatic deaths as supernovae or black holes. Understanding these stellar processes is essential not only for predicting the future of the universe, but also for understanding its composition and structure. Each discovery made by these telescopes brings us one step closer to answering the fundamental question: what will become of the universe? Will it continue to expand indefinitely, or will it eventually collapse in on itself? The data gathered through these cosmic explorations are vital in shaping the theories that could ultimately define the fate of everything in existence. Observing cosmic phenomena like galaxy collisions and star formations provides profound insights into the dynamic processes that shape our universe. These spectacular events not only offer us glimpses into the past, but also give us tantalizing clues about what the future might hold. As we explore these awe-inspiring occurrences, scientists are uncovering the fundamental forces at play, from the violent merging of galaxies to the birth of new stars in nebulae. Each of these phenomena is a page in the book of cosmic evolution. But there's an even more profound mystery at hand, one that challenges our understanding of the very fabric of reality: dark matter. Invisible to the eye and impervious to light, dark matter constitutes about 27% of the universe's mass, yet it interacts with neither light nor any known form of electromagnetic radiation. Despite its elusive nature, it exerts a gravitational influence on galaxies and clusters, profoundly shaping the cosmos's structure and guiding its evolution. For years, scientists have been on a relentless quest to detect this mysterious substance, employing a variety of cutting-edge technologies that may unlock some of the universe's deepest secrets. To uncover the nature of dark matter, scientists have devised innovative experiments, pushing the boundaries of our technological capabilities. Some of the most promising efforts take place deep underground, where sensitive detectors are shielded from the noise of cosmic radiation that could otherwise obscure the signals. These experiments aim to directly or indirectly detect dark matter particles, revealing their subtle interactions with regular matter. Among these ventures, the Cryogenic Dark Matter Search, CDMS, and the Xenon Dark Matter Project, Xenon, stand out. Both use ultra-cold detectors housed in deep underground laboratories. such as the Gran Sasso facility in Italy and the Sudan mine in Minnesota, to minimize interference from cosmic rays. By cooling the detectors to near absolute zero, thermal vibrations are suppressed, which maximizes the chances of detecting the faint interactions that may occur between dark matter particles and ordinary matter. But the hunt doesn't stop there. The Large Hadron Collider, LHC, at CERN, known for its groundbreaking discovery of the Higgs boson, also plays a critical role in the search for dark matter. In proton collisions at nearly the speed of light, it's possible to create dark matter particles, albeit under specific conditions. These collisions produce a myriad of particles, but scientists focus on the missing energy, the energy and momentum that appear to vanish. This absence could signify the presence of dark matter particles, which, unlike normal particles, cannot be detected directly, but would carry away energy and momentum. The potential to create dark matter in these controlled environments offers a tantalizing possibility that we might one day understand this invisible substance through high-energy particle collisions. Meanwhile, our gaze turns skyward, where space-based observatories like the Fermi Gamma Ray Space Telescope are taking their own steps towards solving the dark matter mystery. These telescopes search for indirect evidence of dark matter by identifying gamma rays that might be produced when dark matter particles decay or annihilate. As dark matter particles interact in certain regions of the universe, particularly in areas dense with dark matter like the center of our galaxy or near dwarf galaxies, the resulting gamma rays could act as a beacon to guide scientists toward their elusive quarry. Even more ambitious is the work of the Alpha Magnetic Spectrometer, AMS, mounted on the International Space Station. The AMS scans cosmic rays for irregularities that might indicate dark matter interactions. By looking for anomalies in the cosmic ray flux, an excess or deficit that could point to dark matter annihilating or decaying into regular particles, this cutting-edge instrument provides another piece of the puzzle in understanding the invisible matter that shapes the universe. Looking ahead, the coming era of space exploration promises a revolution in our understanding of the cosmos. With increasingly sophisticated telescopes and missions, humanity is set to probe the deepest reaches of space, uncovering the forces of dark matter and dark energy, understanding the early universe's secrets, and perhaps even learning about the fate that awaits the entire cosmos. At the forefront of this new era is the James Webb Space Telescope, poised to take us further than ever before, allowing us to explore the depths of the universe in ways we've only dreamed of. As it continues to deliver stunning images and data, the JWST is set to change the way we perceive the universe, inching us ever closer to unraveling the enigmatic forces that drive its evolution. The journey has only just begun, and the answers to some of our biggest questions may be closer than we think. The universe, vast and mysterious, continues to reveal secrets that could forever alter the way we understand existence. With its infrared capabilities, the James Webb Space Telescope is already peering back in time, offering a glimpse into the infancy of the cosmos. It's like having the power to watch the birth of a star or the formation of galaxies, helping us unravel the secrets of dark energy and its elusive, enigmatic influence on the universe's expansion. But that's just one piece of the puzzle. The European Space Agency's Euclid mission, set to map the geometry of the dark universe, seeks to untangle the forces that have been shaping the cosmos for billions of years. With an unparalleled focus on dark matter and dark energy, it could hold the key to understanding the very forces that control the universe's fate. In parallel, NASA's Nancy Grace Roman Space Telescope is preparing to redefine how we see the cosmos. With its wide field view, it will examine the depths of space with a precision never before possible, focusing on the same forces, dark energy and dark matter, that are vital to unlocking the future of the universe. This initiative promises to extend the frontier of our knowledge, revolutionizing how we study the cosmos, particularly through its detailed analysis of exoplanets and the vast cosmic structures that surround them. These missions, together with ground-based projects such as the Square Kilometer Array, SKA, and the Vera C. Rubin Observatory, form a powerful alliance that promises to take us closer to answers that have long eluded us. The SKA's vast network of radio telescopes will peer deep into the early universe, exploring phenomena like cosmic magnetism and the gravitational pull of distant galaxies. Meanwhile, the Rubin Observatory's Legacy Survey of Space and Time, LSST, will create an expansive map of the universe, revealing faint objects that could hold the secret to understanding dark energy and matter. These efforts will give us insights not just into the universe's past, but into its potential future, offering a profound look at the forces at play in its ongoing expansion. The Laser Interferometer Space Antenna LISA, another groundbreaking ESA mission with NASA contributions, promises to open an entirely new window into the cosmos by detecting gravitational waves. These ripples in space-time caused by massive events like the merging of supermassive black holes could provide us with insights into the very nature of gravity and the cosmic structure. The discoveries from LISA could forever reshape our understanding of the forces that shape the universe's destiny. Meanwhile, the Dark Energy Spectroscopic Instrument, DESI, positioned on the ground, aims to map the distribution of dark energy across the universe using an intricate 3D map of galaxies and quasars. Through its exploration, we hope to uncover how dark energy accelerates the expansion of the universe, revealing the intricate workings behind this mysterious phenomenon. Together, these initiatives form a scientific revolution, with the potential to map the universe with precision and detail never before imagined. They will answer questions that have haunted humanity for centuries. The map of the universe they create could reveal not only the true structure of the cosmos, but also the origin of the forces driving its ever-expanding nature. As these groundbreaking missions continue to unfold, they promise to push the boundaries of human knowledge, forcing us to reevaluate everything we know about space, time, and existence itself. These projects are poised to uncover new physics that could explain the ultimate fate of the cosmos, offering us a deeper understanding of our place in the universe. Yet, even as we uncover these astonishing secrets, the contemplation of the universe's vastness and inevitable end presents a profound challenge. To confront the cosmic timeline without succumbing to fear is a difficult yet crucial task. It calls for a shift in how we view the end of the universe, not as a terrifying finale, but as a natural part of the cycle of existence. This understanding can lead to a deeper appreciation of the time we have, encouraging us to find meaning and purpose in the present moment. One way to approach this existential challenge is through cosmic humility. By recognizing our small place in the grand scheme of things, we free ourselves from fear. Embracing our interconnectedness with the cosmos reminds us that we are part of something vast, complex, and magnificent. This recognition fosters a sense of awe and wonder, encouraging us to view the universe with a sense of reverence rather than dread. Another way to grapple with the inevitability of the universe's end is by focusing on legacy. Rather than fearing the future, we can channel our energy into making a lasting contribution to the world around us. This shift in perspective, moving from fear of the end to a motivation to create positive change, can inspire us to live fully, to embrace our role in the ongoing story of humanity and the cosmos. What we do now matters. By contributing to knowledge, to art, to kindness, we leave behind a legacy that transcends time, adding to the collective story of all that has ever been. Philosophical and spiritual traditions across cultures offer wisdom on how to approach the universe's impermanence with calm and equanimity. These teachings often encourage us to live in the present, accepting change as a natural part of existence. By viewing endings as beginnings, we can find peace in the cyclical nature of the cosmos, understanding that every creation carries with it the potential for dissolution, and every ending is the precursor to a new beginning. Through this lens, the vast timeline of the universe can be seen not as something to fear, but as an invitation to live more fully in the moment. Engaging with the universe's mysteries through science can also transform fear into fascination. The more we learn about the forces that shape the cosmos, the birth and death of stars, the creation of galaxies, the mysterious forces like dark matter and dark energy, the more we realize how much there is to discover. This pursuit of knowledge can enrich our lives, connecting us not only to the universe, but also to one another. It fosters a sense of shared wonder, a curiosity that transcends fear and propels us forward in our quest to understand the cosmos. Finally, as we look to the future and reflect on the universe's ultimate fate, we gain a deeper appreciation for the present. The cosmos is in constant flux, always changing, evolving. And it is in this continuous state of transformation that we are reminded of the beauty and intricacy of the universe as it exists right now. The future may be unknown, but the present is a gift, and it is this gift that we must cherish, embracing the mystery and awe that the universe offers us at every turn. As we stand beneath the vast expanse of the night sky, we are reminded of the fleeting nature of all things, both seen and unseen. Stars are born, live out their dazzling lives, and eventually fade away, leaving behind the echoes of their once brilliant light. Galaxies collide in spectacular cosmic dances, only to reform into new shapes, new forms of life in the universe. And the universe itself? It is expanding at an accelerating rate, as if racing towards a future beyond our comprehension. This knowledge instills in us a profound sense of urgency. The clock of the cosmos is ticking, and with every passing moment, the mysteries of the universe are slipping further from our grasp. So, what are we doing with the time we have left? How do we use the short span of our lives to unravel the deepest secrets of existence? The quest for knowledge has never been more pressing. This yearning to understand the cosmos also brings us closer to one another. As we peer into the stars, we are reminded that we too are made of stardust. The same particles that once swirled in the hearts of ancient stars now form the very building blocks of our bodies, our world, and everything we hold dear. In the cosmic sweep of time, we are all connected, each one of us a part of the same great story. This understanding fosters unity, urging us to transcend the boundaries that divide us on Earth. It calls us to work together, not just as nations or individuals, but as inhabitants of the same universe. Our exploration of space is not just an intellectual pursuit, it is a deeply spiritual endeavor, one that seeks to connect us with something far greater than ourselves. The more we know about the stars and galaxies, the more we realize how small and precious our planet truly is. And so this journey of discovery becomes a call to action, a reminder that we must push forward together, exploring the unknown, learning from our past, and shaping a future that reflects the best of humanity. But as we contemplate the vast unknowns of the cosmos, the inevitable question arises: what is the future of the universe? How will it end? This question stirs a range of emotions, from existential dread to a more philosophical acceptance. We cannot help but wonder, should we even be concerned with the eventual end of the universe? After all, the cosmic timescales involved are beyond our human understanding. The potential endings of the universe, whether through heat death, the Big Rip, or some other unforeseen scenario, are billions, even trillions of years away. The idea that this vast and ever-changing universe could one day cease to exist is an unsettling thought, but it is a thought for which we have no immediate answers. We must come to terms with the fact that the universe's end is far beyond the horizon of our own existence. For now, the pressing issues lie closer to home: climate change, species extinction, the health of our planet, and the welfare of future generations. These are the areas where our efforts matter most. These are the challenges we can address, not in the distant future, but today. However, our interest in the fate of the cosmos is not merely born of curiosity. It is a testament to the boundless ambition of the human spirit. Our quest to understand the origins, workings, and ultimate destiny of the universe is a reflection of our deep-seated desire to know our place in the grand tapestry of existence. This pursuit of knowledge is not just an intellectual exercise. It shapes our culture, our philosophy, and even our sense of identity. It provides us with new perspectives that can guide us in the choices we make, the way we relate to one another, and the way we approach the challenges of life. Through our exploration of the cosmos, we come to appreciate the vastness of time and space, and in doing so, gain a deeper understanding of our own fleeting place within it. But perhaps the most poignant lesson the universe teaches us is the value of the present moment. The knowledge that stars will one day burn out and galaxies will drift apart serves as a stark reminder of how precious this time is. The cosmos, in all its beauty and grandeur, is in a constant state of flux. What we take for granted today, the life, the beauty, the vibrancy of the universe, is not guaranteed to last, and so we must learn to cherish it, to protect it. The knowledge that the universe will one day end encourages us to live fully, to ensure that the legacy we leave behind is one that reflects our highest ideals. We are custodians of this tiny corner of the universe, and our stewardship of the Earth, of all living things, becomes even more urgent as we consider the distant future. The inevitability of the universe's end also offers us an important opportunity, a chance to embrace cosmic humility. In the face of the universe's grand scale, our petty differences seem insignificant. The realization that we all share a common origin in the stardust of ancient stars, and that we will all face the same fate in the end, has the power to unite us. The cosmos does not recognize borders or boundaries. We are all part of the same cosmic journey, and together we must face the challenges ahead. This awareness can inspire cooperation, collaboration, and a renewed sense of purpose. It can remind us that in the end, it is not our individual survival that matters most, but the survival of the collective, the preservation of our shared home, and the betterment of all. As we near the end of our journey through the cosmos, we are left with more questions than answers. From the birth of stars to the potential rebirth of entire universes, we have only begun to scratch the surface of the universe's mysteries. Concepts like dark matter, black holes, and the ultimate fate of the cosmos continue to intrigue us, pushing the limits of our imagination and understanding. Our exploration of space is far from over. It is only just beginning. As we continue to peer into the unknown, we are reminded of the importance of curiosity, scientific inquiry, and imagination in our pursuit of knowledge. These are the qualities that will allow us to push beyond the boundaries of the known and into the vast, unexplored reaches of the universe. How do you think the universe will end? Will it end in a fiery bang, or will it continue on forever? What are your thoughts on the fate of the cosmos? Share them with us in the comments below. And if you enjoyed this exploration of the universe, subscribe to our channel Starflux for more documentaries like this one. Thank you for watching.